In this work, we describe an algorithm that computes the information an agent is expected to gain by measuring at different locations in a partially mapped environment. Computing such a metric is key to efficient, autonomous exploration. Our algorithm has a lower complexity and is hundreds of times faster than the state of the art, making information-theoretic exploration a practical option for the first time in many scenarios. Autonomous exploration is applicable in a variety of scenarios including search and rescue, space exploration, and environmental surveys. While this task relies on a number of interconnected components like path planning, localization, and mapping, a high-level question that is unique to exploration is, where should I move next? Answering this question requires some specifics, which we will visually demonstrate in the following manually operated exploration. In this work, we consider a robot that is equipped with a sensor that measures distance, like a LiDAR. In this animation, the intersections between LiDAR beams and obstacles are shown in red. Using this device, the exploring robot constructs a map that classifies the environment into regions that are free or occupied. In this animation, white regions are most likely free, black regions are most likely occupied, and gray regions could be either. The goal of the exploration is to make the map as informative as possible. So to clarify, the question our autonomous agent needs to answer is, where should I move next? So that making a measurement with a distance sensor at the location provides me with as much information about the environment as possible. There are a number of heuristics that have been used to answer this question. For example, a classic heuristic, often called frontier exploration, declares that the robot should move towards the nearest frontier or boundary between free and unknown space. Here, we've labeled the frontiers in red. This strategy does make the robot explore, however, it doesn't necessarily do it efficiently. In this example, a robot is faced with choosing between two passageways. Even though exploring the left passageway will clearly be much more fruitful than the right, frontier exploration doesn't discriminate between the two. To make the most informed decision, we need to be able to measure how much information the robot is expected to gain. This metric is the focus of this work. We've displayed it here where the brightness of each pixel indicates how much information the robot is expected to gain about the environment by making a measurement at that location. The most informative locations to explore are the most bright. More precisely, this measures the mutual information, I, between the map represented by random variable m and the sensor measurement represented by random variable z made at position x with field of view theta. Mutual information has been in autonomous exploration literature since at least 2002. However, it hasn't seen much practical use because computing it has been thought to be computationally intractable. The state-of-the-art CSQMI and FSMI algorithms can compute the expected information gain of a single measurement location with a time complexity that scales with the time it takes to cast a ray from that location across the map, as shown in this one-dimensional example. However, the time to compute the information gain at all possible measurement locations grows quickly. In this paper, we present the Fast Continuous Mutual Information Algorithm, FCMI, which recursively reuses computation so that the expected information gain at all cells can be computed in a single pass. These results generalize to 2 or 3 dimensions by casting rays in multiple directions and accumulating the results. One of the main contributions of our work is modeling the map as a continuous field rather than a discrete grid. Although it is not entirely necessary to provide the recursion that results in performance gain, it makes deriving those results much easier. Moreover, it reveals and corrects subtle but important issues in existing algorithms such as initialization scaling, anisotropic effects, and volumetric overcounting. In particular, previous algorithms operated on a discrete grid where each cell is labeled with a probability of being occupied. These algorithms can be derived from the fact that the probability a curve does not hit any obstacles is equal to the product of vacancy probabilities of the cells the curve intersects. In our work, however, we assume that the space is continuous, and that each point in the space has an infinitesimal vacancy value. the probability a curve does not hit any obstacle is equal to the continuous product of vacancies along the curve. Using that model, we derive a continuous expression for the probability density function of a single distant measurement beam. This in turn produces a continuous expression for the differential entropy of that measurement beam. And finally, the differential entropy can be used to compute the mutual information. The recursive aspect of our algorithm comes from the fact that the probability density function can be defined recursively over regions with constant vacancy, like occupancy cells. With everything defined continuously, this recursion can be propagated through the equations just listed to get a recursive formula for the mutual information as a whole. The exact mechanics are in the paper. Our experiments show that the FCMI algorithm can compute the expected information gain at all cells in a map in mere seconds on a single-threaded CPU. This is hundreds of times faster than the state-of-the-art FSMI algorithm. In this final example, we show the metric being used in a simulated exploration experiment. At each step, the exploring agent is propelled towards the point maximizing mutual information times a function that decreases exponentially with distance.